Hello everyone, I hope all of you are doing great and staying safe. On behalf of Petro, Arab Oil and Gas Academy and SPE Egypt section, I would like to welcome you to our second interesting webinar about machine learning fundamentals and introduction to Python. This course consists of 4 webinars, 4 quizzes, and the final exam. First, let me introduce myself. My name is Salma Rashidi. I'm a petroleum engineer. I owned my bachelor's degree from the American University of Ras Al Khaimah, and I'll be the moderator for today's session. Our lecture today will be delivered by a very special and knowledgeable guest. Mr. Belyadi is a senior data scientist and engineer at Vine Oil and Gas. He's the founder and CEO of Obsertelligence, focused on providing artificial intelligence, in-house training, and solutions. He served as a faculty member at multiple universities, including West Virginia University, Marietta College, and St. Francis University, where he taught data analytics, natural gas engineering, enhanced oil recovery, and hydraulic fracture stimulation design. Mr. Belyadi has over 10 years of experience working in various conventional and unconventional reservoirs across the world. He has worked on various machine learning projects and held short courses across various universities, organizations, and the Department of Energy. He is the primary author of Hydraulic Fracturing in Unconventional Reservoirs, first and second editions. He is the author of Machine Learning Guide for Oil and Gas using Python. He has authored and co-authored several SPE papers. He holds his bachelor's and master's degrees both in petroleum and natural gas engineering from West Virginia University. So basically, he's a living legend. So please make the most out of this lecture. If you have any question, please don't hesitate to drop them in the Q&A box. Mr. Belyadi, we are so honored to have you today, and the mic is yours.
Thank you very much, Salma. Appreciate that. And thanks to Petro and everybody, including Dr. Ahmed, who has organized this really good webinars for students across the world. Welcome back, everybody. Last lecture, we talked about all the fundamentals of machine learning. We talked about the workflows. And before we get started, just one more time, if you haven't subscribed to the podcast, the Obsertelligence podcast, please do so. These are just educational free podcasts that are on YouTube, where I invite different professors and also different executives and ask them about their vision of data science and artificial intelligence within the oil and gas industry. And all the materials that we'll be covering in this course will be coming from this book here, in case you haven't noticed. And with that being said, last time we talked about cloud computing and basically data centers. If you recall, we talked about different types of data centers. We talked about the traditional data centers, like centers, the on-prem data centers, and also the cloud data centers that a lot of the major organizations such as Amazon and Microsoft provide. So if you remember, just a quick overview of that is that cloud computing revolves around large centralized servers stored in data centers, and these data basically are processed and then travels to the central processing center. So one thing that I want to mention is that you can actually go, for example, on Amazon and actually have a free access to free cloud computing. They have different tiers, and one of the tiers is actually free. It doesn't allow you to have a lot of storage and a lot of CPUs, but it is free. If you want to get kind of hands-on, you can actually try that. And now, for you guys starting out, you can use we're going to talk about installing Python and how you can go through that process. But you can actually use your desktop to run different codes, because you're probably not dealing with huge amounts of data. Once we go into a large amount of data, then I think that's when you need to start actually using cloud computing to help you fasten the process. But if you're gonna use a few spreadsheets that have 200,000 rows, 100,000 rows, your desktop can most likely manage that, and you don't need to go to cloud computing route. But if you're gonna do like seismic interpretation and terabytes of data or gigabytes of data, then that's I think when cloud computing can really help you fasten the process. So we talked about cloud computing. Now let's talk about edge computing. So as I said, cloud are basically like, these are the data centers that different companies have, such as Amazon. AWS is a famous cloud provider by Amazon. Azure is a famous cloud provider by Microsoft. So aside from cloud computing, there's another term these days called edge computing. Okay, edge computing. Now, what is edge computing? So let's first talk about what edge is and what the reasoning behind using edge would be. Okay, so edge basically are small computers. Think as edge as small computers, usually like this size. And basically these edge computing or these edge computers or these edge devices are designed for harsh environment. Okay, they're designed for harsh environments, and especially in the oil and gas field, where you go out and place these edge devices. It's in, like, a lot of places are super cold or super hot, so these edge computers are designed for harsh environments, and the ones that are not designed for harsh environments are actually encapsulated into a box, so they'll be protected. But that's what an edge computers are. They're basically small computers that are designed for harsh environments, that are used to data. It is used for real-time data processing, and what it does, it allows for machine learning models to be deployed on those edge devices. Okay, so if you recall, last time we talked about supervised machine learning model, unsupervised model. We talked about reinforcement learning model, right? So these models, let's just say you develop these models and you're interested in deploying some of these models real time. Well, how do you do that? Well, to deploy these models real time, you need to actually couple that model with an edge device in order to deploy real time. And that's when the advantage of these edge devices come in. So you can actually deploy these machine learning models and couple them with an edge device. And basically, the advantage of these edge devices is that they make real-time decisions for you. So as opposed to waiting a few days to make decision, you can make real-time decisions and autonomize the whole field. And that these are the advantages of some of the advantages of edge devices. So as you can see, this is critical for technologies such as real-time applications, allows for efficient data processing, and large amounts of data can be processed, and reducing internet bandwidth, and then it eliminates costs and ensures that applications can be used effectively in remote locations such as oil and gas sites. And as I said, these edge devices are great for remote locations, because they're specifically designed for harsh environments. So basically, again, these are the same stuff that we talked about. Just remember the difference between, the cloud computing and the edge computing, that, there are two different things, and the terminologies, that are used are not the same thing. So just remember that edge devices are installed on site. Okay. And these are just mini computers or small computers that are designed for harsh environment. And you can deploy your machine learning models on those edge devices for real-time decision making. If all you can take from edge devices, that's all I want you to take from it. Just you can deploy your machine learning models on those edge devices for real-time decision making to create value, and that's the value proposition of edge devices. And as we go, into there are a lot of companies, including Dell, like, for example, that produces these edge devices in large amounts. As the use of edge devices become more common, the cost, of course, is going to go down. So in the next, I think, few years, you're going to see a lot more momentum from edge devices in the oil and gas industry for autonomous and automation, basically. So the next slide that I want to talk about, as you guys can see, we talked about artificial intelligence. We said this is basically using machine intelligence as opposed to human intelligence, right? This is artificial intelligence, or they call it AI, right? And then we talked about machine learning. We said it's a subset of AI. As you can see here, You got the artificial intelligence, and you got machine learning, which is a subset of AI. And we talked about what machine learning was, and how, what the use of machine learnings are, and some of the techniques, the different techniques, different types. We talked about some of the algorithms under each type, if you recall, and some of the basic workflow that we talked about, right? That was machine learning. And then there's another term called deep learning. If you guys haven't heard that before, you hear that term a lot. So if you listen to, for example, a lot of the executives from major tech companies, if you listen to Eric Schmidt from Google, he always talks about deep learning, how powerful it is. If you listen to different executives from Amazon or Facebook, they always talk about deep learning, and so what is deep learning? And in this class, we're not going to go too deep into deep learning, but just understand that deep learning is basically a form of neural network. Okay, is a form of neural network, and basically what deep learning does, as you'll see in a minute, in a neural network, you have one hidden layer. In deep learning, you could have multiple hidden layers. Okay, so you have more than one hidden layer. And basically, there are different types of algorithms under deep learning, such as a recurrent neural network. This is one form of deep learning algorithm, which is very sophisticated and very powerful. It is used for time series analysis. We talked about that. There's another type called convolutional neural network. Those are also very powerful for image processing, for text processing, for seismic, especially for seismic data processing. Convolutional neural networks are also very powerful. So if you remember anything from the slide, remember the artificial intelligence, you got AI, you got machine learning under AI, and you got deep learning under machine learning, or deep learning is under artificial neural network. And basically it just means that you have a neural network with multiple hidden layers, and it's very powerful in extracting data. So now the next slide is, why is deep learning or in general neural networks have become very powerful or very common? This is nothing. Neural networks have been around for decades. They're nothing new. It's not like it was invented a couple years ago. So why all of a sudden, deep learning has become, or neural network with combinations of deep learning have become very powerful and very famous all of a sudden? Well, the reason for that is, one is big data. We now have large data sets. We have easier data collection and storage techniques, right? We have big data. And when you have a lot of data, these deep learning algorithms become so powerful when you have a lot of data. So now that we are starting to track and store and have a lot of data, these deep learning algorithms really become very powerful. So big data is number one. Hardware, we have GPUs now, graphics processing units. Your computers probably have CPUs. GPUs now is the next generation of computing, and you can see that you can use you can actually get a computer that has GPU and basically run your codes based on that. And actually, you can when you install these deep learning packages such as TensorFlow and Keras, you can actually you can actually run those packages with your GPU of your computer as well. So with the advancements in hardware such as GPU, it really allows for deep learning applications within different industries. And also the last one that I wanted to talk about is software. Now you can see TensorFlow. If you look at TensorFlow, is a powerful package provided. You can actually download these packages in Python or in your Anaconda. Like your Anaconda doesn't come with TensorFlow, but you can install that on top of that, and it will actually you can use this to run deep learning models very easily. So you have all these softwares that have been generated now to run these deep learning algorithms, which are very powerful. So that's why in the past, few years, or in the past, I would say 5 years, deep learning has gained a lot of momentum, just because, we have big data now, we have the hardware, and we have the software. Okay. So now let's talk about artificial neural networks. So to understand deep learning, we have to first understand what artificial neural network is. And we're going to go over actually a little bit heavy on math today and talk about what ANN does, and go through the steps. It's actually, once we go through the math, you see how easy it is. Actually, they've made it sound very complicated, but it's not. So I'm going to explain what ANN is first, and then go over the math step by step, so you can understand what exactly an ANN does. And this is going to be the whole lecture today. And this is so important. ANN is one of the main algorithms used in machine learning. And also, on top of using ANN, all the deep learning algorithms, such as the convolutional, the recurrent neural network, all of those, you have to first understand the fundamental building blocks of a perceptron, of a neural network, before you go into the deep learning algorithms. Okay. So what is ANN? As you guys know, human brains have billions of neurons. Okay, has billions of neurons, and it's very complex. Our brain is very, very complex. And in my mind, when I think about some of the complexity of the neural network of human brain, I always think about how hard it is to how hard the psychology of people is, right? Because every neural network is different, right? And there are billions of neurons, and so it just goes to show that how complex and how powerful humans are in general, with this ANN, or artificial neural network, that we have. Okay. So the idea from ANN came from the neurons of the brain. Okay, it tries to mimic the human artificial neural network. Okay, so there are different types of so each artificial neural network consists of an input layer, a hidden layer, and an output layer. And we're going to talk about each one: an input layer, hidden layer, and an output layer. Okay, and then the number of neurons in the output layers, also the number of neurons in the hidden layer, is a function of how complex the problem is. So the more complex the problem is, the more neurons you're most likely going to need. Okay, so if you're solving a pretty easy problem, you're not going to need many neurons in your hidden layer. But if you're solving a pretty complex problem, then in those cases, you're going to need a lot of neurons. And in some cases, you might need multiple hidden layers. You might need more than one hidden layers, which is then you're going into deep learning, right? So as I said, when your data becomes so immense, and extracting information from that data becomes very difficult, you're going to need a lot of, you might need a lot of neurons, and also multiple hidden layers to tackle that problem. So with that, let's just look at this example here. Let's look at, here's your input layer here. You have your, for example, your input features, like gas in place in this case, sand per cluster, water per cluster, number of perfs, stage spacing, cluster spacing, and so on and so forth, right? These are your input. This is your input layer. And then you have one hidden layer here. This is just one hidden layer. Okay. And then you have an output, it's a regression output. It's a regression model, because your output is EUR, is estimated ultimate recovery per 1,000 feet. Essentially, it tells you how much the well produces over its entire lifetime, right? It's your EUR per 1,000 feet, of lateral length. And as you can see here, there is a cost function here. This cost function is simply the average differences between your actual values and your actual values and your predicted values. So if you take the average differences between your actual minus predicted values, That's the loss function that you're trying to really minimize in an artificial neural network. And we're going to go into these calculations a little bit more deeper in a minute. Okay, so just remember that in an ANN right now, you have an input layer, you have a hidden layer, and you have an output layer. And your output layer in this case has just one output, which is EUR per 1,000 feet, but you could have multiple outputs. Okay. So now let's talk about. Here we go. Let's go over the fundamental building blocks of a neural network. So let's look at this and make sense out of this first. So first you have your X1, X2, and XM. These are your input, basically your input features, right? Like sand per foot, water per foot, or let's just say cluster spacing, and so on and so forth. And there is a weight associated with each input feature. So you have W1, W2, let's just say WM, okay? And then what you do is, so you take each input feature times a weight, okay? Times a weight, and then you sum it up. You sum it up. Then you also add a bias. A bias is basically this W0. This W0 is basically your bias, and what it is, it allows your activation function to move to the left or right. And by the way, bear with me, I haven't even defined activation function yet, but just bear with me for 1 second. So you have your X1, X2, XM, you have weight 1, weight 2, and weight M, right? And then you sum it up, you add a bias, then what do? Then you apply a nonlinear activation function, okay? And we're going to talk about different types of activation functions, different types of nonlinear activation functions. And then that's it. And then you get your output. So your Y hat is your output. This is this symbol here is your nonlinearity or your nonlinear activation function. This is your summation. And then these are your weights. And this is your inputs. This is the basic form of a neural network, and I haven't even added the hidden layer yet. But when you add a hidden layer, it just the process continues the same exact way. So let's just look at the inputs. You got the weights, summation, nonlinearity, and output. So if you take anything from this slide right here or from this whole lecture about ANN, is that what ANN does? It takes each input features, multiplies it by a weight, okay, and then it sums it up, okay. This summation here. Then it adds a bias, okay. This bias allows your activation function to move to the right or left, okay, and then take the activation function of this whole term basically. And that is basically the fundamental building blocks of a neural network. So this is it, guys. I mean, this is really it, how simple actually it is. It's not that complicated. Your inputs times your weights, sum it up, nonlinearity, output. This is the fundamental building block of a neural network. And to understand, other forms of neural networks and other deep learning and other stuff, we first have to understand this basic concept here. So very important. Just remember, you got to take your inputs times your weights, sum it up, add a bias, apply a nonlinearity, and then you get your output. So now let's go to the next slide. So again, the next slide is the same thing. What we're doing here is you have your inputs times your weights, then you sum it up, you add a bias, you take the activation function of this whole term. Now let's rewrite this using more exotic term, using linear algebra, okay? Let's rewrite this in this form, and this is the form that you might see in a lot of the books, in a lot of the places that you go to. So basically, G is your nonlinear activation function, which is here. W0 is your bias, which is here. Plus, instead of this summation of xi times wi, what I did was I just converted this to a vectorized form, so I have X, capital X, and then I have the capital W. And capital X is simply X1 through XM. And then capital W is basically your vectors, W1 through WM, okay? So this is the form that you see in a lot of these, in a lot of the textbooks. And if you read an article online, this is probably the form that you're going to see. But simply, this form here is just a linear algebra version of what I showed you here, basically. Okay, it's the same exact thing. So now, what is this nonlinearity? We talked about this nonlinear activation function. And what is it used for? As you guys know, nonlinearities allow us to approximate arbitrarily complex functions. Okay, that's what nonlinearity allows. Just look at this picture. Look at this x and y. And if you're trying to capture this nonlinearity, this data, you cannot capture this data with just a linear function. So that's what a nonlinear activation function does. It captures nonlinearity in complex functions. And this is just one simple example of what that means. Okay. So now just remember that, in a simplified version of perceptron, by the way, neural network is also referred to as as MLP, multi-layered, perceptron, or like a neuron is simply a perceptron. Okay, so don't get confused with the terminologies here. Okay, so as we said, to simplify this whole thing, you can see that you have your inputs. Okay, you multiply it by the weights, you sum it up, you add a bias term, you apply a nonlinearity, and you get your output. Okay, so this is basically a simplified version of this is the fundamental building blocks of a neural network. So now let's talk about when you add a hidden layer. Okay, when you add a hidden layer, what happens? And I think the best way to go through this is to go through an example on how this is actually done. So I have one simple example that goes through step by step on exactly how you do it. So you train a model. As soon as you train a neural network model, what happens is it's going to give you all the weights and all the biases, okay, for that neural network model. So assuming that we have trained a model now, okay, let's go over the calculations here. So here's the example. So the example says an ANN classification model with 5 input features and 1 hidden layer that includes 11 hidden neurons have been trained with high accuracy. The resulting weights and biases have been summarized for each feature and neuron. Apply this trained model to the input matrix provided. Use the logistic function, which, by the way, we'll talk about. This is logistic function is an activation function that we haven't talked about yet, but we'll talk about after the slide here. For transformation, and classify the result less than 0.5 as good and more than 0.5 as bad, since logistic functions fall between 0 and 1. So here's a table that I have. So I have parameter A through parameters E. E is an echo, okay? As I said, in this case, the structure of this neural network has only 11 neurons. As I said, the more complex the problem is, the more neurons you're going to use. The less complex the problem is, the less neurons you're going to use. But in this case, I said, let's just use 11 neurons just for this example. So I have neuron 1 through neuron 11, okay? I also have parameters A through E, and each parameter has an associated weight for each neuron. So parameter A has a weight of 7.54 for neuron 1, okay? Parameter A has a weight of minus 2.36 for neuron 2, okay? Parameter C has a weight of minus 16.96 for neuron 5, okay? And then, so you can see that each single parameter and each single neuron has a weight associated with them, okay? Now let's talk about bias. So this is the bias term. As I said, the bias term allows the activation function to move to the left or right, right? That was the whole point of the bias. So from your trained machine learning, artificial neural network machine learning model, you also get a bias associated with each neuron, okay? Associated with each neuron right here. So neuron 1 has a bias of 1.86. Neuron 5 has a bias of minus 0.29. Neuron 11 has a bias of 6.38. As I said, this is just an example with just 5 parameters. You could have 100 input features. You could go A through 100 features, or you could have, thousands or hundreds of thousands or billions of neurons, as far as my concern. But as the number of neurons increases, the complexity also increases, and the time it takes to run these models also increases. And by the way, if you have too many neurons, your model might just get overfitted, and we'll talk about overfitting and underfitting in a minute. Okay, so these are basically provided to you, right? This is provided to you. Now let's go and look at remember that you have an input layer. In this case, you also have a hidden layer with 11 neurons, and then you have your output, right? In addition to the first set of weights, you also get the second set of weights, which are 10.83, minus 12.33, and so on and so forth. You also get your last bias, which is 1.24. These are all from your trained neural network machine learning model. And then these are your input features. You have you have parameter A through parameter E. Parameter A, so you're trying to evaluate what happens, to this set of features. You're trying to predict what happens when you feed the model a new data point. And the new data points are 7890 for parameter A, 94 for parameter B, 0 for parameter C, 0.006 for parameter D, and minus 0.09771 for parameter E. So you're trying to evaluate what happens when you feed the model these new set of features in terms of your prediction. Is it going to be good, or is it going to be bad? In this case, it is a classification problem. And you can see here you have parameters A through parameters E, and these are the min and max feature of each parameter. So the min is 6447, the max is 13827, the min is 10, the max is 104, the min is for parameter C is 0 and 4.12, and so on and so forth. So why do I have this min and max provided here? If you recall from my last lecture, what I said was we first have to normalize these parameters. When you feed in all your features into a neural network model, you first have to normalize your features to be on the same scale, to be between 0 and 1. Okay, so the first step that I have to do is I have to normalize this input parameters to be between a scale of 0 and 1. So the first step is, here's the first step. So I take each feature, 7890, which comes from here, 7890 minus the min, which is 6447 of parameter A, divided by max minus min, which is 13,827 minus 6447. Here we go. So x minus min of x divided by max of x minus min of x for each parameter. So parameter A, normalization. Now I've converted this to a scale between 0 and 1. So it's 0.1955. Same thing for parameter B. I'm going to take 94, which is the input parameter that is given to me, 94, minus 10 divided by 104 minus 10. So if you remember, 10 and 104 came from here. It's your max and it's your min. So I'm going to just normalize each feature individually. Okay, that's the first step that I got to do. Because this problem, when it was provided to me, it did not include the normalization. So I have to first normalize the feature to be on the same scale between 0 and 1, and then move on. Okay, so I did the same exact thing for parameter A, B, C, D, and E. That's step 1. Loud and clear, right? So step 2 now. So step 2 is the matrix, if you remember, is the matrix multiplication of the normalized input parameters from step 1, right? By bias and weights of each neuron. So let's just think about these numbers here. You see this 0.1955? This came from here. 0.1955, 0.8936, 00, and 0.046. 0.1955, 0.8936, 00, and 0.046. So these are my input features. And if you remember, I said you multiply your input features by your weights. Your weights, remember that? Your x1 through xm times your w1 through wm. So you multiply that by the weights right here. So the 7.54, where did that come from? Let's go back to the input problem. Here we go. 7.54 minus 1.83 minus 9.59. These are the weights of your neurons, of neuron 1. Okay, so here we go. Minus 1.83 minus 9.59, and so on and so forth. So, and this term here is your basically your bias, you know, 1 and 1.86, you know. So so if you do that matrix multiplication, it's just 1 times this plus 0.1955 times 7.54. You just do the simple math here, and then you get a value of 2.22. So now you got to do the same exact matrix multiplication between your input features and your weights for each one of the neurons. This was for neuron 1, by the way. For neuron 1, you got 2.22. Do the same thing for neuron 2, you get minus 0.27. Do the same thing for all the neurons, and you get 6.09. You can do this. You can either code this in Python, or actually, you don't even have to code this in Python. If you feed Python your new set of features that you want to evaluate, it will spit out the result for you. But I'm trying to make you understand how Python does it, or how any other programming languages goes through the process of step-by-step calculations. Okay. So this was step 2. So step 1 was normalization. We normalized the features to be between a scale of 0 and 1. Step 2 is a matrix multiplication of what? Matrix multiplication of your input features times your weights. Okay. Now, step 3, you apply a non-linear activation function. That is your non-linearity, a non-linear activation function. So if you remember, in the previous step, the neuron, the matrix multiplication turned out to be 2.22 for neuron 1, right? So 2.22. So a sigmoid activation function basically says 1 divided by 1 plus exponential to minus x. And this x is simply your minus 2.22. That is your sigmoidal activation function. That is your logistic activation function, which we'll cover right after this example is finished. So you can see here, 1 divided by 1 plus e to negative 2.22, and you get 0.9019. And you do the same exact thing for each neuron. So you apply the sigmoidal function, or the logistic function. For neuron 2, you get 0.4321. For neuron 3, you get 0.5403, and so on and so forth. So remember, step 1, normalization. Step 2, matrix multiplication of inputs and your weights, and then you sum and then add a bias and sum it up. That's right here. Then step 3 is applying a logistic function, applying a non-linear activation function to that term, which we discussed, right? And here's that. Now, step 4, now we have to take the outputs, which are, if you can see 0.9019, 0.9019, and multiply it by the second set of weights. So if you remember, the 10.83 came from here. See this? 10.83. 10.83 came from the second set of weights, which are basically after your hidden layer, right? This is the this is right before you feed into the hidden layer and you go into the output, right? So you have to take and you have to do a matrix multiplication between these second set of weights and what came out of this step 3 here. So you take 0.9019 times 10.83 plus 0.4321 times the second set of weight for the second neuron, and you do the same exact thing until you get minus 3.5439. So that is step 4, which is the matrix multiplication of the last bias and the second set of weights. And then, as you might have guessed, the next step is to apply a logistic function to that. So when you apply a logistic function, which is 1 over 1 plus exponential negative 3.5439, which came from this guy right here, then you get 0.02808. So since 0.02808 is less than 0.5, the classification for this input set of data would be good. So this is how basically you can predict when you train a model, when you train a neural network model, you can then predict what happens when you receive a new set of features, what happens to those to the prediction of that set of features. So you can see here in this case, since the answer was less than 0.5, it turned out it was classified as good. If it was more than 0.5, it would have been classified as bad in this case. So just an overview of this example. This example basically showed us that each neuron has a particular set of weights, okay? Each parameter in each neuron has a particular set of weights. And also it has the bias. In addition to this, if you have one hidden layer in your network, you also have the last biased and the second set of weights here. These are essentially received from your ANN model. And then the first step that we did was we have to normalize the features between 0 and 1 because the input features that were provided to us were not normalized. These were the original forms. So we normalized the features first. Then we took the input features, which were the normalized features here, and multiplied them by the first set of weights. If you remember, your xi times your w, or your x1 through xi times your w1 through wi, right? And then you applied a logistic nonlinear activation function to each one of the neurons, and here are the results. Then you did a matrix multiplication of the resulting answers from step 3 to the second set of weights. You did the matrix multiplication again, and you got negative 3.54. And the last step is to apply one more time the logistic function or the nonlinear activation function to that minus 3.54, and you got this answer here. So this is an example of how you can actually predict once you train your machine learning model, once you train your neural network machine learning model. So we talked about the activation functions. There are different types of activation functions. And these are some of the most commonly used ones that you can see here. You have the identity activation function, which is simply f of x is equal to x. You have your logistic activation function, which we just covered in the previous example. It's just f of x is equal 1 divided by 1 plus exponential to negative x, And this is the logistic function that we used in the previous example. And it's a pretty well-known activation function that that a lot of the problems use to solve. Okay, so this is one sort of activation function. Another type of activation function is tanh. It's simply your tangent hyperbolic activation function, and then you also have your arctan, your inverse of tan activation function, and binary step, which is another type of activation function. So there are different activation functions, and so you might be saying, Haas, which one do I use? There are so many activation functions. I don't even know why you chose logistic activation function versus tanh activation function, right? So that's, if you recall, in the last lecture, I talked, one of the students asked about how do we optimize these hyperparameters? And the answer was grid search. If you remember, grid search optimization is a process where you run different combinations of different fine-tuning parameters to see which one results in the best accuracy. So for example, if I'm trying to optimize which activation function to use, well, I would have to run logistic activation function with different set of neurons, different set of solvers, different set of learning rates, different set of momentums, and so on and so forth, to see which activation function results in the highest testing accuracy. So what you can do is you can run a grid search optimization, which is essentially a nested for loop that goes through logistic activation function, tanh, arctan, identity. It goes through different activation functions and run those activation functions with different hyperparameters to see which activation function results in the highest accuracy. So in short, you can actually find the best activation function for your problem based on running different iterations of those hyperparameters. Okay, so that's how you find the best activation function for your problem. Okay, so this is how you get your activation function. Now we talked about loss optimization, right? We talked about in a neural network, you're trying, the objective function is to minimize your loss function, right? Is to minimize your loss function. Well, and we talked about that loss function is simply the average between your actual values minus your predicted values, right? You're trying to minimize that. So how does that work? Let's look at this picture here. So on this axis here, you have your loss function with respect to a couple of weights, weight 0 and weight 1. Here's your weight 0 and weight 1. The objective function is to try to, you're trying to go from this top of the, let's just assume this top of the mountain. You're trying to go from top of a mountain to the bottom of the mountain, okay? To go from top of a mountain, imagine you're blindfolded and you don't see anything, okay? You're going to take one step at a time, either a small step or big step, right? And the size of the step, varies, right? If you're more brave, you can take a big step. But if you take a big step, then what happens? Then you might miss on some of the other steps. If you take two of a small step, it might take a long time to get to the bottom of the mountain, right? So the idea behind a gradient descent is that you start from top of a mountain and you take the gradient, okay? And then based on that gradient, you slowly try to find your way to the bottom of the mountain, okay? So that's what gradient descent is. So the objective in neural network model is trying to finding the weights, the network weights that results in the lowest loss. So let's actually go back to this slide right here. This slide right here. So let's just say I have my sand per cluster, I have my water per cluster, I have my number of perfs, I have my stage spacing. I'm going to feed into the model with these set of weights. I'm going to get, for example, an EUR. The predicted EUR is, let's just say, 1.5 BCF per 1,000 feet. However, my actual EUR is 1 BCF per 1,000 feet. So my predicted is 1.5. My actual is only 1, right? So there's a 0.5 BCF difference. What does this do? What is this? What is this neural network is going to do then? Well, this neural network is going to back propagate, and change the weights of these neurons. You know, the weights that I just showed you. You got to change the weights of these neurons, okay? And then spit out the output again. Now the output could be, let's just say 1.2. Well, that's closer now. Your actual was 1.5. Your predicted is 1.2. Now that's a 0.3 BCF per 1,000 foot difference. It's going to back propagate again to this hidden layer. Back propagate by changing the weights of your neural network, and then spit out the result again. Now your result is 1.4, and the predicted was 1.5. Now it's a 0.1 BCF per 1,000 foot difference, much closer, right? So it's going to keep iterating, keep doing this process until this loss function that I just showed you is minimized. Remember, this loss function is nothing complicated. This loss function is simply the difference between your actual minus predicted, just the average of those. So if your actual was 1 BCF, your predicted is 1.5 BCF, that difference is what? Is 0.5 BCF. And for the second set of test set, if your actual is 1.2 and your predicted is 1.3, that difference is 0.1 BCF, right? And then continue on and then take the average. That is basically your loss function. That's basically you're trying to minimize this loss function. So when the model in neural network, you're going from input to your hidden to your output, right? It's a feed forward model. It feeds forward all the way into your output layer. Okay. So now in back propagation, that's where the complexity comes in. In back propagation, it back propagates into your previous layers. So it back propagates from output layer to hidden and to your input, changes the weights, and then it spits out a new answer. And then it compares the new answer with the actual value. Is it getting closer, or is it getting further apart? Then it continues on with these iterations. It continues on and on and on until this loss function is minimized, until it gets to a point that as you keep adding, as you keep changing the weights, this loss function does not drastically get decreased. It decreases slightly. It doesn't have that much impact. Okay, so at that point you're good. At that point, life is good. You've selected the optimum set of weights for all your neurons, and you can continue on. So remember, if somebody asks you, feed forward propagation is just, it goes from your input layer to your hidden and to your output. It's a feed forward neural network. Back propagation is when you go back and change the weights of these neurons that we talked about, and then spits out the result, compares it with the actual, and it keeps going on the process until the process is finished. Okay, so now let's go back to the gradient descent I was talking about. So remember this loss, so this JW0 and JW and W1 is your loss function, okay? And then this is your simply your weight 0 and weight 1. So now let's look at the steps in a gradient descent. In a gradient descent, you initialize the weights randomly. You randomly initialize the weights. Like here, for example, again, I'm going to start going from the top of the mountain to the bottom of the mountain. Okay, I'm going to initialize the weights, for example, right here. Or you could go right here, or anywhere that you want to, right? And then loop until converge to a local minimum. So what happens is now what you do is you calculate the gradient. And the gradient of what? You calculate the gradient of your loss function with respect to weights. So if you remember from this picture here, you're calculating the gradient of the loss function with respect to W0 and W1. These are your two set of weights that you have here. If you have more than two set of weights, you calculate your loss function with respect to all of your weights, right? That's what a gradient descent does. So you compute the gradient. If you don't remember what gradient is, I'm sure you guys have passed the calculus course. You go back to the fundamentals of gradients and how it works. So you basically take a step in the opposite direction of gradient, which is essentially going down, right? So you're taking a step in the opposite direction of the gradient here. You're going down. And then what happens? Then you update the weights, right? You calculate the gradient, then you update the weights, and then this eta here, this eta parameter here, this is called your learning rate. Your learning rate is basically the size of the step that you're taking. So if you go from here to here, it's just basically called your eta, or your learning rate is the size of the step. If you take small size, it might take a long time for your model to converge. If you take big step sizes, or if you assume big learning rate, it might jump over some of the important information that you might miss. So you want to optimize that learning rate as well. And again, optimizing the learning rate comes from what? It comes from the grid search optimization, okay? It comes from the grid search optimization. And actually in Python, you can also assign an adaptive learning rate as opposed to a fixed learning rate. You can assign an adaptive learning rate where the model changes those step sizes over time as a function of the number of iterations in your neural network. So that's how this learning rate actually works. And then you update the weights until your loss function is minimized, right? Until this gradient here. Remember this gradient of loss function with respect to weights until this whole term is minimized. Then once your loss function is minimized, then that's your answer. You might be asking, Haas, how do you calculate the gradient in backpropagation? Well, that comes from chain rule. Chain rule in calculus, you can calculate your gradient in backpropagation. Okay, so I hope this makes sense. I know we went through a lot of math, but remember that if you want to understand, for example, go to deep learning, understand that you first have to understand a simple neural network. You first have to understand the fundamentals of neural network prior to going into a backpropagation type of, or prior going into deep learning type of algorithms. Okay, so that's why I really wanted to hone in and go in more depth as far as what is exactly happening behind the scene. That way, when you start using Python, when you start applying these models, you know exactly what's what, which parameters to fine tune, which parameters to work on, and so on and so forth. So now, remember that learning rate determines how fast the weights coefficients are basically updated. Learning rate varies from 0 to 1. And if the learning rate is too high, as I said, the algorithm might miss out on important steps and fail to converge. If it's too low, it might take too long to reach its destination, which is minimizing the loss function, or also they call it the cost function. It's the same thing, the loss function or the cost function. So with that being said, I'm going to stop right here. This was basically what I wanted to cover today. I wanted to cover the edge computing and also go into the steps behind a neural network and how it works, and go through the calculations on that. I hope this makes sense. You might have to watch this video a couple of times if you didn't get it for the first time. And I can assure you that after watching a couple of times, you're going to start to understand the process and the calculations behind neural networks. But just if one thing that I want to say, that I want to mention to remember, is just remember the slide here. You have your inputs, you have your weights, you sum it up, you add a bias, you apply a nonlinearity activation function, which we talked about. You have logistic activation function, 10H, and all those activation functions. and then you get your y hat, which is your output. So with that being said, I'll take any questions that you guys have.
So, Hoss, I have a question, if you don't mind.
Yeah, sure.
So, what is the requirement to be to be an expert in artificial intelligence, and you can make money out of it? What should be? Am I must be engineer, or or what kind of a specialty? If I want to take it as a business.
Okay, as a business, I think one thing that I would say is you first have to have some type of passion for it, right? If you don't have any passion for, statistical analysis and dealing with numbers and looking at data, then it's not for you, right? But if you're passionate about it, if you're truly passionate about it, like the reason I do this, because I love what I do, I would first hone in on the fundamentals first. First, learn the fundamentals of what is happening behind the scene. It's super easy now to go on, for example, on Python and just apply, load in different libraries and basically apply different, machine learning like algorithms within Python. Is super easy now, like nowadays. But first, you have to understand the fundamentals behind what you're doing. And then once you understand the fundamentals, then you can move into learning how to code and learning how to apply these techniques for solving real-time applications. So I always tell people, always first learn the fundamentals, understand what you're doing, because if you don't learn the fundamentals, it could be dangerous, right? You're going to go in there like blindfolded, and just running different models without knowing what the model is doing, how it's converging, whether you've reached your local minimum, whether you've reached your optimal solution. Applying those models without any type of background will be very difficult. So my first recommendation is to learn as much as you can about the fundamentals, and then move into coding. And then, the last piece is simply the application of it in Python. It's a free open source. That is super easy. You can use Python, you can use R, you can use Julia. There are different type of platforms for those type of applications.
So sometimes we get this question. Someone say, "Hey, I have the passion. I want to learn, but I almost know nothing about programming. I know nothing about artificial intelligence. So how long it takes to consider yourself like an expert?
Yeah, so the expert honestly comes from years and years of experience. You cannot just learn this. I mean, you can learn the stuff, if you studied for 10, 12 hours a day, in 6 months, you could be up and going. But until you actually apply these techniques to real world problems and solve real world problems, and provide a value proposition, that's when I would call you an expert. Because using open source data sets that have been, provided to you for that purpose to use for just practices, anybody can do that, right? But the next step in your mind should be, okay, which areas of my study can I apply this to? Can I apply this to, for example, solving a problem in drilling engineering, in completions engineering, in production engineering, and that's when you have to kind of hone in more on, what is the value proposition of actually like applying this to provide value for the organization.
Okay, it seems like we received another question. Someone asking, do we need a software for this course other than Python?
Yeah, as I said, you can use different softwares like R, Python. You can use MATLAB to run your machine learning models, but you don't need any other softwares besides Python to run this. You can do everything in Python. You don't need to. You're more than welcome to learn different programming languages. I actually encourage that, but you don't need to. We're not going to use 2 different languages. In this course, we're just going to get some introduction to Python as far as how you can just do run some basic code.
Well, that's a wrap for today. Thank you, Mr. Belyadi, and thank you all. The lecture will be uploaded to PyPetro YouTube channel. Don't forget to solve the quiz on Google Classroom. Thank you again, and see you next Saturday.